In the beginning, there was the noise, and the noise was without form. The entropy went to infinity. And then humans said, let there be signal. And there was signal. And the signal was good. And human called the absence of signal 0, and the presence of signal 1. And data was born. And by combining the data into an organized form, that data became information. And that information, when combined together, was able to be recorded and passed along. And so over time became knowledge. And then eventually that knowledge was interconnected, and it began to converge towards something we might call wisdom. And so that brings us all together. We're now here in this place. Actually, more specifically, you are here. I'd like to take this opportunity to say grazie mille a tutti gli organizzatori. Thank you so much to the organizers, to the staff, to all of you. Let's give them a big round of applause. So this is life, the universe, and everything go. And I am Dead Program, also known as Ron Evans, technologist for hire at the Hybrid Group, where we create the software that makes your hardware work. And some of us do some labors on an open source project you may have heard of called TinyGo, the Go compiler for small places. But this is supposed to be a talk about innovation. Just one little problem. No one can tell you how they do innovation. Now, you might be thinking, who's this Dead Program guy? How does he know anything about this subject? Well, there's this, I mean, really, I'm not kidding. No one knows how to do innovation. How do I know? Well, there's this little company called Intel that I used to work with that gave this award for top innovator in 2015. Also 2016, 2017, 2018, and 2019. Here's a picture of me with former Intel CEO, Brian Kazanich. Okay, so as part of this, I actually did get to meet some real innovators. Lots of people are out there doing innovative work. And so you speak to them and you ask them, so how do you do it? No one can tell you how they do it. No one can tell you how they do it, or no one will tell you how they do it. The reason, of course, is very serious people. You know very serious people, the ones who approve budgets, head counts, do your annual review, make important decisions, the very serious people of the world. But once those people have left the room, as they inevitably do to go to bed early, you'll find out they will admit to you the whole time the people who are doing innovative work were just playing around. All right? Now, to the serious people, play is a 4-letter word, right? Like, do not say I was playing around during work hours, or, well, you might be reprimanded. But play is actually our superpower. If I leave you with nothing else today, I want you to believe in the power of play to maybe accomplish very serious things. It's contradictory as it is. So let's just have a quick review of a few forms of play. Music, we play music. Games, we play games. Programming, we play with programming. So a few quick questions. Is music a game? Well, the formal definition of a game is a form of play that follows a structured set of rules. So by that, music is a form of play that follows a structured set of rules to do with musicality, so it's probably a game. Is programming a game? Yes, I think it may be. Is making a game a game? Yeah, we got meta-programming already making its first appearance. Is music programming? That way we complete the tetrahedron. Well, Aya Beder said the most interesting things happen at the intersection of disciplines. She's a genuine innovator, the creator of Little Bits, a really amazing piece of hardware for teaching kids about technology, electronics, and programming. So let's talk about a few innovators. John Coltrane, one of the greatest musicians of all time, but not just that. He actually was fascinated with the geometry of music. He spent much of his time making hundreds of drawings like this one, only a few of which still survive, preserved by the musicologist and saxophone player Yusef Lateef. This is his tone circle, where he geometrically represented the different relationships between the music that he was playing. This is one of his most famous compositions, Giant Steps, and we can see that the relationship of the different chord changes follows a very exacting form of geometric progression. So, very interesting ideas coming as to what play can represent. The rules of play. So this is Alan Turing. He doesn't really look like a very playful guy, does he? Maybe one of those serious people. He presented area when needed. So a lot of people know about the Turing test, which was actually called by him the imitation game. And that's information that people now know because of the name of the movie of the same name, but up until then, people just called it the Turing test. Turo Champ was actually the first computer game. They never were able to get it to execute, but it was a chess playing program that was actually able to defeat the human opponent. It was written entirely on paper. And then the Turing machine, his theoretical computational machine, which in fact he never built. It was only theoretical. So talk about playing with ideas. But interestingly, let's take a quick peek at one idea, what's known as Turing complete. You've heard this phrase a million times. You probably don't want to admit you don't know what it actually means. I feel the same. So usually Turing complete is, they say, when some computational system can be used to implement the same computation in terms of itself. That's just way too recursive of a definition for me to follow. It could be more simply stated as that it's a computational system that can do loops, that can have some form of conditional, some sort of if-then, and is able to store the result of a computation. Just with those three things, that is actually a more, easier to grasp definition of Turing complete. So the play is the thing. This is John Horton Conway, a guy who spent most of his career playing, despite being somewhat famous in the mathematical world. In fact, when he was a student at Cambridge, the laziness doctrine was one, he was much more likely to be found playing backgammon or making up games with his friends, the math chums, than actually working on his PhD thesis. Along the way, though, he came up with knot theory, which is explanation for all the different mathematical forms of possible knots. Surreal numbers, which I actually can't try to describe to you right now. And the game of life, which is the thing that Conway became most famous for, even though that somewhat bothered him because he thought it was the least of his accomplishments. But it was one of the most interesting. Let's talk about the game of life. So the game of life is actually in the category of things called cellular automata. And they were come up with about 20 years earlier by the famous John von Neumann, who was also a character in his own right. But it didn't really catch on. People were like, you didn't have any computers, even though really Conway didn't have computers either. But the zero-player game, that means that it plays itself. Once you set it up in any particular form, the game just plays itself and you see what happens. So how to play? Start with a grid. Each square is a cell. A cell can be either alive or it can be dead. So then we go through and we look at each cell and we count the number of neighbors that that cell has. And then we apply some rules to that particular cell. So there's a birth rule, which says any dead cell with exactly 3 live neighbors becomes alive. So it becomes birthed. The survival rule, which says any live cell with 2 or 3 neighbors lives on. And then the death rule, which says any live cell with fewer than 2 live neighbors dies. and any live cell with more than 3 live neighbors dies, like overpopulation. So here's a quick look at some of the outcomes. You see in the middle, we've got this center cell, the blue one. So the blue one only has 1 neighbor, so it dies. In this case, the blue one has 2 neighbors, so it lives on. In this case, it has 3 neighbors, so it lives on. Here it has 4 neighbors, so it dies, and so on. So interestingly, the game of life is Turing complete. That means we can make a computer out of a game. In fact, a couple of years ago, some teams had a competition, and Tetris was implemented in the game of life. So we're not going to do that today. But let's go play with life a little bit, shall we? And since we use Go, let's do it with Go. So let's start with, what if life was a command line application? Right? So if life was a command line application, it would be hello life. And so hello life, let's take a look at the code for hello life. So hello life is a Go program. It brings in a couple of standard packages, buff.io, funt.os, and it brings in the game package from the Acifan Vita library. More on that in a minute. So the first thing we do is we create a new universe, which is a 16 by 16 grid. Then we randomize it so that basically there's a 45% chance that any cell will be alive or dead when we first start the game. We'll print a blank line. We'll print which generation it is. We'll print out the universe so we can see the state of it. Then we'll say universe.tick. Universe.tick moves our universe forward so that we can see what the next state of the universe is going to be. So as we tick forward in time, we see the game play itself play by play. And I'll pause in between each so we can press enter to continue so we can see what it's actually doing. All right, so let's take a quick look at the code. So like, make hello life. Okay, so there we see generation 0. There's generation 1. There's generation 2. Let's start hitting through it. You can sort of see patterns starting to form. It's actually sort of looking alive. Okay, so there's hello life. So we got some of the ideas. So we saw the demo. A brief note on the Vita library, created by Alessandro Cifani, who's unfortunately not here. I think some of his colleagues are, but collaborated with me on a lot of these demonstrations and the creator of this library, so grazie mille. Let's take a quick look at some of that code, just so we can get an idea. So here's the universe in code. So it's got a height, a width, the cells, and of course, the rules. So when we create a new universe, the default will be using Conway rules. Conway rules? Well, the Conway rules are that we're going to apply rule B3S23. So in the world of people who are life hackers, there is shorthand. This says that B3 means you're born if there's 3 neighbors, and S23 means you survive if there's 2 or 3 neighbors. So we're going to apply rule B3S23 as our default, and then we're going to use this more neighbors. More neighbors is basically going to go and take a look and say, for any of the different neighbors we've got, we don't want to look at ourselves. We're going to go to the left, our same row, and to the right, and column, and we're going to go through and count the number of neighbors. Okay? So, but what if life was a client-side browser application? Because isn't that what's like so cool now? Isn't that what everybody's doing? Well, we'd have browser life. So browser life, of course, is written using WebAssembly and Go. We've seen some great talks about WebAssembly, so I won't really go over those details, but the browser engines that are built into all the standard browsers already have WebAssembly runtimes built in. So on your, you've got your JavaScript engine, and you've got separately this WebAssembly engine that you can call from JavaScript. So in the case of this web app, there's a web page. It's got some HTML form elements. It's got an HTML canvas element where we're going to draw the game of life. And then through a little JavaScript interface, it's going to call into a compiled vita.wasm file where we're going to be able to communicate with our game universe, and that's where we're going to store the state. So a quick look at the Vita code for the web app. So here's the main app, and it creates a universe and randomizes it, just like we saw before. But now in this case, we're going to connect to the JavaScript environment, and we're going to use the JavaScript rendering loop to actually draw the universe and then to advance its TIK. So it's the same thing, and then eventually draw it in the form of that HTML canvas. Okay, so let's take a look at the demo. So let's see. Actually, the easiest way will be just to go to the website. So there's Game of Life in the JavaScript browser. And we can reset it and then randomize again. We could change the number of cells when we randomize so that there's fewer or more, which kind of doesn't work that well generally because it dies almost instantly. You can't even see it. There's also an interesting concept, which are basically there are forms. There are certain predefined forms which reach a sort of static state. Like you see these spinners. Well, one of them is called a glider. And it's literally just a glider that keeps its form until it runs into something, and then everything starts evolving and mutating around it. It's almost like it's alive. Well, you know, we're using TinyGo for this to create the WASM, because TinyGo is so much smaller. This is my one flossing about the size of TinyGo's smallness. So I compiled this using BigGo, and I also compiled it using TinyGo a couple of days ago. So with BigGo, it was 1.8 megabytes for that code, and with TinyGo, it was 71K. So you might want to check out TinyGo if you do any WebAssembly stuff, especially in the browser where you have to download it. All right. So what if life was a programmable badge? Do you ever wonder that? I wonder those sort of things all the time. Well, we'd have badge life, of course. So let's talk about microcontrollers. They're those little chips that are in all the devices you use. Let's go over each one of these boxes one by one. No, just kidding. This is just sort of a conceptual diagram of a microcontroller is generally delivered in the form of what's called a system on chip, or an SoC. And it's got the processor along with some of the needed connections and circuits to do particular kinds of input-output, turning LEDs on and off, being able to read buttons, communicate with different sensors, displays, and all those sorts of things. So in TinyGo, we have a thing called the machine package, which is our hardware abstraction layer, which lets us communicate with all the different hardware, like over 100 different boards, and in the TinyGo drivers package, over 100 different displays and sensors and other types of devices. So the machine package is our hardware abstraction layer. So for this demo, I'm going to use the Gopher badge created by my wonderful colleague, Conejo, who's here in the audience, who did a great talk earlier. The Gopher badge has got a Raspberry Pi RP2040 microcontroller. It's not a full Raspberry Pi Linux computer. It's just a single chip. It's a dual-core ARM Cortex-M0 that runs at 133 megahertz. And this particular board has 8 megabytes of flash. So the hello world of things, just so we can see that, so we know what we're seeing before we get to the life. So we have our machine package and the time package. We're going to use the built-in LED. We're going to set it to an output and then turn it off. Wait 500 milliseconds, turn it back on, and then repeat that. So it should have a blinky LED. So let's see if we can make this work. Oh, first let's turn on our video. I think I need to take off my lens cap. This is why I'm not a professional photographer. I always forget to do that. Oh yeah, that's better. Let's make that a little bigger so we can actually see. Okay. And so here is the Gopher badge. Whoops, upside down. Well, good. Here is the Gopher badge. And so we're going to plug it in so we can flash it with the code. with the LEDs on the back here. Make hello things. It's going to flash it with a Go program, which will then cause the LED to start blinking on and off. And there we see the LED. It's a little out of focus. Let's see if we can improve that slightly. That's a little better. So first demo of hardware, success, yes. We've just begun, my friends, we've just begun. All right, so now that we've seen that, let's take a look at badge life. Oh no, that sounds amazing though. Will you do that again when I point to you? All right, so badge life is, of course, life running on the badge. So once again, we're going to bring in our game package. We're going to have our universe. We have our game.newUniverse. We randomize it. We say go start game. You know, we can run Go routines even on tiny little 32-bit microcontrollers with TinyGo. We're going to have our buttons. This way I can push the buttons to do some different things. When I push the A button, I'm going to randomize it. When I push the B button, reset. That way I have the same controls as the web interface, just because like, I'm kind of obsessive like that. And then, so let's go and oh wait, let's take it, before we do that, let's look at what the display does. So the display brings in the TinyGo drivers package where we have all the support for the different displays and other type things. And again, the game. So we're going to have our little cell buffer, and we're going to open up the serial peripheral interface or the SPI interface, the display, configure it, fill the screen up with a filled color. Then we have a game buffer. So we have a little slice of bytes. That way we can have a nice smooth display rendering if the game is not, Go routine is not operating as quickly as the display. That way it looks nice and smooth. And then we tick forward through time as we did before, and we sleep for 10 milliseconds to give the thing a chance to see if anybody pushed the button. All right? So let's go for badge life. So again, it's flashing, and it's going to show us the size of the program, which in this case is a bit bigger than the other one. It's actually 11K to do this. And there's badge life. Life running on the badge. The lights are right, and that's a little better. Oh, it's reached a pause. Let's start it up again. Pretty smooth for kind of chip that's usually used for telling whether your refrigerator door is ajar. All right, badge life. So that, of course, brings up the question, what if life was a GameCube? I mean, so we'd have cube life, of course. So cube life, we'd have a cube. So each side of the cube, though, we should have it be a parallel universe. Right, man? Like, I swear this made sense that we're talking about it with Elon. So the way, though, we'd have to be able to tell the neighbors, because the universes, they're not actually connected, so we'd have to go over to the adjoining neighbor universe to be able to tell. Otherwise, they're just disconnected from each other, and if we don't have a multiverse, then this is a very boring movie. So in the multiverse, of course, since it's written in Go, we're going to, how do we have concurrent things communicate in Go? Well, we use Go channels, naturally. So we have, each universe is going to have a send and a receive channel, because that way they can communicate with each other as to what the state is, and they can tell whether or not the neighbors are actually close enough. So for this, see, I didn't realize there actually was a GameCube. I know I messed up, I guess, kind of out of touch, I forgot. So it's actually an LED cube that uses an Adafruit Itsy Bitsy M4 processor with 6 Hub 75 displays. So the Itsy Bitsy M4 is a microchip, ATSAM D51. So it's a little bit more powerful than the Raspberry Pi. It's got an ARM Cortex M4, 32-bit processor. Runs a bit slower at 120 megahertz, but it only has 192K of RAM. So 192K of RAM. That's what we're talking about here. So it's got these panels, the Hub 75 LED panel. These are the panels. I've got one here that's not connected. Oh, yeah, this is the cube, by the way. So these panels, you connect to them through, here's the power, and then these ribbon cables. And then, I'll show you the other chip. This is an itsy bitsy M4, just on a breadboard. You can see it's very small. There's one inside here. I didn't really want to open it up in the middle, just because if I break it. So we use some advanced techniques in order to do all of this on a single controller. Direct memory access being one, and interrupts another. We don't really have time to go into what the details of those are, but suffice to say that's what's necessary to keep up this much concurrency on such a small, low-powered chip. So let's take a quick look at cube life. How are we doing for time, by the way? Time and space. Okay, so cube life, once again, we bring in our game package. So we've got our multiverse, which is a slice of parallel universes. And we're going to have basically dead, and then red, green, and blue colors. You'll see why when we get to that. So when we create the multiverse, then we connect them all up to each other. And then our for loop is we draw the cube, then we save the state of the buffers, run the universes forward, and then every second we'll display stats, and then once a minute, we'll reset the whole cube because there's no buttons on it. I didn't want to have to worry about how to deal with that right before this talk, so seemed like the easiest thing. So when we create the universes, we're using what's called the parallel universe. So parallel universe is something else that we had to create, but let's get into that later. I already explained pretty much how that worked as far as that it's got well, actually, might be, well, let's keep going. So the parallel universe is using channels to communicate between the different, actually, I can show you that. That's in here. Can I? Yes, okay. No, actually, that's not. Well, never mind. Let's keep going. We don't have time. Lots of time, little to do. Wait, strike that. Reverse it. All right. Cube life. So let's see if this is actually going to work. So far, cube life. Can we flash the cube? This is a 36K program. Oh, yes. Cube life. So we can sort of, let's see where there's anything interesting. Oh yeah, there's some interesting stuff happening there. You can see where they're jumping between the universes. An invasion, a colony, you make the call. Yeah, some interesting stuff happening here. Yeah, so each one of these is a separate Go routine, but on a single processor. So we're definitely pushing to the limit of what this processor can do. And you can see here that it got into some of the figures, the spinners. Oh, wait, here comes some other life to take over. Oh, there's still some things happening over here. In just a little bit, it will reset. How will you know? Oh, you'll know. It's an extinction event. It's just been colonized by a new life form that evolved. So don't worry, life will continue on the GameCube. Cube life will continue even if the original one goes extinct. So you've got that to comfort you at night. All right, let us continue. So what if life was a serverless web service? Doesn't this keep you up at night? Okay, I mean, it does me. Well, you know, cloud life as a service. So I think it's pretty obvious with the events of these last few days that this whole artificial intelligence thing is completely played out. Okay, it's over, done. Who would want simple artificial intelligence to have artificial life instead? Isn't that like a better deal? Wouldn't you prefer to have artificial life? So life as a service. So we would implement this in the form of using the WebAssembly System Interface, or WASI. And we heard a couple of great talks. Philippe gave a great talk, Francisco, on the first day. And Conejo also used WebAssembly System Interface earlier today. So I'm like just following a well-trodden path. So in this case, though, the way it works is that we don't have to run in the browser. We can run our compiled WASM code in any of a number of different runtimes. We can use WASM time, which is written in Rust. We can use WA0, which is pure Go. We can use WASMer. There's a whole bunch of different runtimes. And we use Fermyon Spin. So Fermyon Spin uses the WASM time runtime, and it's a cloud service. Lets us run serverless functions that are written in a number of different languages, including Go by way of TinyGo, and execute them in the way of serverless functions. So here's the cloud life architecture. The multiverse, of course, responds to HTTP endpoints, as multiverses tend to do these days. I mean, you got to have a RESTful API to the multiverse. And it also then has a separate component of universes. Each universe has its own HTTP endpoints, which then communicate with the distributed universe type. And the way that we actually track state across this distributed multiverse is using a simple key value store, which is one of the services which is built in to Fermyon Spin. So let's take a quick look at some of the code. Here's the Cloud Life logo, just because, we got to establish our brand early on. Let's take a look at the multiverse first. Well, actually, first, let's take a look at the spin.toml. Really, it's to be YAML. Someone forgot to tell them if you want to be cloud native, you have to use YAML. So, I don't hold that against them. But you define each component and what WASM file will be used, what the command is going to be. So you could actually combine TinyGo with Rust or a couple of other languages in a single application, but I'm not going to try to do that today, just because that's a little too much for one demo. But let's take a look at the multiverse. So the way that the things work in Spin is that you define these Spin handlers in the case that you want to be receiving HTTP endpoint triggers. And so first we're going to open the key value store. Then we want to make sure we close it when we're done. So for our post event, we create all of the universes by calling this create universes. When we get, we just return the state of all the universes. Put advances the universes along by calling multi-tick, which is calling universe.tick on all the universes in the multiverse all at one time. One master plan controlling all the multiverse. God, that's so exciting. All right, and of course, delete all universes because, it's like that when you have this sort of divinity programming fetish going on. All right, so create universe is going to make an HTTP call to the universe. So each universe is actually its own universe, right? Independent, operating, able to communicate with and get state from. So it's got its own HTTP handler. So when we post, we create a new distributed universe. When we get, we display the state of the universe. When we put, we advance the universe along by one. And you'll notice here that we have to create a new universe, and then we load its state in, the state that was saved in the key value store. Yeah, I forgot to mention, it's a stateless distributed universe, right? That's very, very important. Otherwise, how would this work? And then, of course, the universe can be deleted when we're done. So let's take a look at what will happen if we play with the universe. Actually, let's turn off the video, because we don't need that anymore. All right. So if I make cloud life up, it's going to call spin build, which then is going to compile the two modules, the two components, the first one being the multiverse. And you'll notice it's using TinyGo build target WASI, GC leaking. Yeah, TinyGo, you can actually have different garbage collectors. So we're going to use one that never deallocates, because with the serverless function, why bother? Like, it's just get in, do your biz, exfiltrate. Oh, no, that's something else. And then the same thing. So now we've got our routes available. So let's use that internet tool that is the tool of choice, curl. Yes, all right, so let's say curl, and then let's post to the multiverse. All right, so we just returned the identifiers of, how many, 16? Yeah, 16 universes in the multiverse. And if we forget what those are, remember we can HTTP get, so we can see what they are. Oh yeah, okay, cool. Notice they're in a different order, just because it's a key value store, so we don't necessarily have any sequence guarantee. So now if I say put, so that advances all the universes by one and then displays them, right? So I mean, if we scrolled up a bit, we could see it is a multiverse after all, even though it's made of 16 separate universes. So we have some idea now of what we could do, but that's a terrible way to control your multiverses, right? I mean, don't we need more sophisticated tools? Well, of course, that's why we have life control. I heard that was how you control all these things in the cloud. So life control, of course, is a command line tool. It is part of the Cloud Life package, so it comes along with the single price. So it is written using UR-Fave CLI, which is one of my favorite tools for doing CLIs. So it's got a couple of different commands. We've got the start command, if we want to start up some different multiverse. It's got a stop command, and then it's got a run command. So the run command is very interesting because it calls Go routines to tick all the universes forward. And the way that we keep them all synced up, of course, is using a wait group. This way we can make sure that we don't keep calling the universes independently, and we keep them all together with the purpose of maybe displaying them or doing something with that. And then tick universe just calls our HTTP endpoint as we would expect. So, but of course, we said cloud, right? So we need to deploy something to the cloud, because otherwise it's like not that cool. Right? Oh, wrong window, wrong tab. B0. Okay, love tmux. So, make Cloud Life deploy. So let's deploy to the Fermion cloud the latest WebAssembly modules that I just compiled earlier. So it's going to deploy to the cloud. And now it's ready at cloudlife.fermion.app. So now if I run life control, so we can control our Cloud Life. So let's see, what were the commands again? Ah, yes. So let's do life control start, passing it the host, because you're going to have your own multiverse to use this. Don't just put it on my bill, please. We're going to start 8. That means start an 8x8 grid of multiverses, so 64 simultaneous universes. So let's start those up. Oh, failed to start. Off to a good start. Maybe we should stop before we start. Oh, yes, that's always good. Okay, so let's start up those 8. Not the fastest of internet speeds, but it should do. All right, so there's our 64 universes in the multiverse. So now let's call run. So now run is calling all those different universes independently through those wait groups. And so we're able to see that we're actually getting more than 300 universes per second on average, nearly 5 multiverses per second. So, that's quite remarkable. Eventually, when we do the Tetris in Game of Life, which I didn't have time to actually do for this, because we're going to do something else in a minute. So yeah, it's amazing the things that we can do. So there's life as a cloud serverless application, Cloud Life. Well, what if life was actually life? I know it's the only frontier left. What if life was actually life? We'd have human life. So we're now going to learn a sonic language, us humans in this room. So please stand up, everybody. And try not to leave any gaps because you saw how the grid works. All right, so the first thing we're going to do is a vowel sound. So vowels are like, it could be an ah or an o or an oo. So, and then, so in one moment, we're all going to make a sound of a vowel sound, and then in order to finish, I'm going to do this, which is like a typical conductor of choirs thing to mean stop. Okay, so a vowel sound, ooh, ah, anything you want. 1, 2, 3, 4. Where's the oohs? Wow, you guys all were in choir, weren't you? All right, so that's the first one of our sonic language. Our second is a sibilant. So a sibilant is a sound that's like an S, like a S, a hiss or a sh. So it could be anything you want. It could be like kind of, you know, sort of Jimi Hendrix. You know, like it's whatever you, it could be like whatever you want. So practice your sibilant. 1, 2, 3, 4. The wind cries Mary. Excellent. Okay, that's the second in our musical vocabulary. The third is a percussive sound. So a percussive sound, it could be like a golf clap, or it could be like beating your chest or snapping your fingers. It's any, you know, kind of percussive type sound that you want. So try not to hit anybody much. Okay, 1, 2, 3, 4. Oh, yeah. All right, we got this. So now let's play the flag game. So I wasn't actually able to get flags, so instead I got these kind of like poles. So let's see. The orange will be the vocal sound, so let's start that over here with you. And the yellow is going to be the sibilant, so let's start that back here with you. And then this, of course, will be the percussive sound. So let's start that over here with you. I know, you're wondering how you're going to be percussive while holding it. Now, hold it straight over your head. Okay. Now, the way that the flag game works is if you are right around the person with the flag, the baton, make that sound. So make the vocal sound if you're right around that person. Make the sibilant sound if you're right around that person. And make the percussive sound, okay? And then pass the baton to anybody you want that's right around you. Remember, only make your sound, or that sound, in case it comes over, right? Just remember which one is vocal, sibilant, percussive, right? So as it passes around, only the people right around it. Okay, are we ready? 1, 2, 3, 4, begin. Hold it up high so people can see it. Pass it, man. Keep passing it along. I know, it's hard to pass while percussing. No, I can't play it. Hold it up high. Okay, and stop. Now, that was great. So now we're going to play the advanced flag game. Okay, now hold up your flag. Okay, now let's see. That was the vocal. That was the percussive. Okay. Say the color. Yes. Orange is vocal. Green is percussive. And the yellow would be the sibilant. Right? Good enough. The advanced flag game is the same as the flag game, but without the flag. Let me have those. I know. Same exact thing, though, right? So how are you going to pass it? You're going to have to listen. You're going to have to use one of those senses. Okay? So advanced flag game. 1, 2, 3, 4, begin. Okay, so now that we've trained our biological neural network, now let's play Conway's Game of Life. You know the rules by now, right? I hope. All right, so let's see. Who are going to be cells? Let's see. Vocal cell, vocal cell, vocal cell, vocal cell, vocal cell. Then we have to go start back here. How about sibilant, 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 sibilant? You see, I'm trying to make a glider. Let's see if it works. And then percussive, let's go percussive, 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 percussive. Okay, so remember Conway's Game of Life. We all remember the rules, right? So if you are not making any noise, and there are 2 people around you making that noise, right? Birth, B2, S23, you survive. Keep making the noise of 2 or 3 people around you. If nobody around you is making a noise, make no noise. If everyone around you is making noise, stop making noise. All right, are we ready? 1, 2, 3, 4. Okay, let's randomize and restart. Do whatever you want, but follow the same rules. So just start out making any sound you want, or talk to the people around you real quick in the next 5 seconds. So let's randomize the board, try again. Okay? Any of those 3 sounds following the same rules. Are we ready? 1, 2, 3, 4, begin. That was amazing. Was that fun? Give yourselves a round of applause. Who needs cloud computing when you have biocomputing? So the place as you'll go. Well, we can use Go for command line applications. We can use it for browser applications with WASM. We can go on microcontrollers. We can go serverless with WASI. We can use plugins with WASI, as we saw in a couple of demos earlier. Salud. We can use Go for cloud infrastructure. Yeah, you knew that. Like, that's been done. But we could use Go for other things, safety critical systems, perhaps. We could use Go for machine learning. Actually, some of us already are. We could be using Go for bioinformatics. We could be using Go for energy storage systems. Go for some problem that needs solving, okay? Because the future is actually looking kind of serious. I don't know if you've noticed. And we need new ideas, and we need them now. So I know we've come a long way. We're changing day to day, but tell me, where do the children play? Those are the lines from a great song from Yusuf Islam, formerly known as Cat Stevens. And that's it. Time to go.
Thank you so much, Mr. Owens.
I'm not going to take any questions, but you can come up and get some swag and take a closer look at the cube.
Thank you again. You didn't even let me introduce you earlier. I was ready to introduce you, and then you started all along. You came in.
Amanda needs no.
No, of course, you didn't need it. Okay, thank you again. So please stay with us because we're going to have our final speech, okay? Thank you again to everyone for coming. It was very good to have you all here, seeing so many people gathering together, sharing their knowledge, their passion. So thank you again for these 3 days of conference, 2 days, no matter when you came in. So let's give ourselves an applause, yeah? I think we need it.